Welcome to video number 86 in our series on tensor calculus. In this video, we're going to develop what's known as the Theorema Egregium. This is a very important relationship that establishes the connection between the Riemann tensor and the extrinsic curvature tensor that we analyzed in previous videos. What we're going to do is to apply the commutative operation to the shift tensor. So we'll start by expanding out the full meaning of the operation. On the right-hand side, we'll make use of the rules we learned in the last video. We know we're going to need a separate term for each surface index. Well, there's only one surface index, omega. We can ignore I because that's an ambient index, so we're only going to need one term. But omega is in the lower position, so it's going to be a negative term. So we have negative r, and the contraction is going to be with this index, which means we'll need a dummy index up here. Then the index here is omega, then alpha, beta, then our shift tensor with the dummy index to complete the contraction, and I remains unchanged right up here. Now in video number 74, we ran across this expression. The covariant derivative with respect to beta of our shift tensor zi alpha is equal to the normal component in I times our curvature tensor with indexes alpha and beta. Well, what we can do now is to replace this expression right here, which is this form, with this form. Now to do that, I'm going to rename alpha to omega, of course, but I'll also switch the order of the indexes. So we'll have covariant derivative with respect to alpha of Ni times b beta omega. So what you see is that this term right here is the equivalent of this as per this expression down here. Now this term is the same as this one, except it's negative and alpha and beta have been swapped. So what we can do is simply copy this term over here, making it negative and switching alpha and beta. Well, what we have now is a product of terms, so we'll apply the product rule to expand this out. What we'll have is the covariant derivative with respect to alpha of our normal component in I, and that times b beta omega, and then we'll add the normal component times the covariant derivative with respect to alpha of b beta omega, like this. And so these two terms right here taken together are the equivalent of this one term. Now again, we can complete the expression just by taking this, copying it over here, making terms negative, and swapping the values of alpha and beta. Referring again to video number 74, we have Weingarten's formula, and that was the covariant derivative with respect to alpha of our normal component in I is equal to the negative value of our shift tensor zi beta contracted with our curvature tensor with an index in the upper position and the lower position like this. So what we can do is to replace this expression here with this, but I'm going to have to use a different letter than beta because beta is already in use, so I'll use lambda instead. So this is negative zi lambda times b lambda alpha times b beta omega. And this term remains unchanged, of course. And as before, we can complete the expression by copying these terms, reverse the signs and swap the values of alpha and beta. Now this relationship is rather interesting on its own, but the real value comes when we find the normal and the surface projections of this equation. So that's what we'll do next. To find the normal projection, we need to contract both sides of the equation with ni in the lower position. Now as we do that, recognize the fact that ni contracted with our shift tensor zi lambda is just going to yield a value of 0. And that comes from what we learned back in video 63, that this is really just another way of expressing this fact, that the dot product between n hat and our basis vector s lambda is equal to 0. These are orthogonal to each other, and these are equivalent ways of expressing that relationship. Well, that means as we go through this equation and dot everything with ni, this term, and this one are all going to go to 0 because of this particular fact. Now, also, of course, ni, the lower position, dotted with ni in the upper position is going to yield a value of 1, and that means that these two terms, this one and this one, are going to become 1s. So when we dot everything with ni across the board, we're going to be left with only two non-zero terms. And there'll be this. There'll be this first term of the covariant derivative with respect to alpha of b beta omega, and minus covariant derivative of with respect to beta of b alpha omega, and the right hand side is just going to be 0. So we can move this to the other side of the equation, and when we do, we're going to be left with what's known as the Codazzi equation. The main significance of this result is that this expression is symmetric with respect to these two indexes. We can swap alpha and beta in this expression. But of course we already know that our curvature tensor is symmetric, so we can swap these two as well. And that means that we can swap these, beta and omega. So the expression is totally symmetric. To summarize, if we take the covariant derivative of our curvature tensor, we'll get a third-rank tensor that is totally symmetric. All right, well this is interesting, but what we're really after is going to be found when we find the surface projection of this equation. So let's move on and do that. To find the surface projection, we're going to contract both sides of our equation with the inverse shift tensor, sigma I. Now, when we contract this term with this one, with our shift tensor, zi lambda, we're going to get a Kronecker delta. You remember that we have a contraction along the ambient index, and that leaves us with a delta factor, in this case of delta sigma lambda, like this. Okay, well, when we contract this term with our normal ni, the inverse shift tensor, z sigma I with ni in the upper position, we're going to get 0. This, again, comes from video 63, where this is just the equivalent of the dot product between n hat and the contravariant basis vector, in this case, s sigma, like this. And these are orthogonal, so the result is 0. These are just two different ways of expressing that same fact. Okay, well, that means that as we go through the equation, here, here, and here, we're going to get this delta factor, and here and here, we're going to get 0. So we'll have three non-zero terms left, this one, and this one. So we'll have negative delta sigma lambda times b lambda alpha, b beta omega, and then we've got this term right over here. That's going to give us a plus delta sigma lambda b lambda beta times b alpha omega, And both of these are zeros, and we're left with this term over here, which is negative r lambda omega alpha beta times delta sigma lambda. All right, well, to clean this up, we'll divide out our factors of the Kronecker delta here. We'll switch sides of the equation, change all the signs to make this positive. We'll also lower the lambda index in each term. And when we do that, the result we get is going to be known as the Theorema Egregium. Theorema Egregium is a Latin expression meaning remarkable theorem. So what is it that makes this theorem so remarkable? Well, first of all, if we look at the right-hand side here, we see all of these curvature tensor factors. Obviously, the relationship is about the curvature of the manifold. And the fact that we have equated this with our Riemann tensor tells us straight away that our Riemann tensor must carry information about the curvature of our manifold. But beyond that, the factors over here are derived from extrinsic information. Remember, we call this the extrinsic curvature tensor. We derive these values from things like the normal, the tangent space, the tangent plane, that sort of thing. So all of this is a result of understanding how the manifold was embedded within the ambient space in order to derive the curvature information. On the other hand, the Riemann tensor is an intrinsic object. Remember that it is derived from Christoffel symbols and their first derivatives, and those in turn are derived from the metric tensor. And the metric tensor is an intrinsic object. It's something that you can figure out without any reference to extrinsic objects. Our friends Bert and Ernie could go through their manifold, taking measurements, they could map out a metric tensor, and from that they can come up with a value for the Riemann tensor and in turn get the information about the curvature of the manifold. So what this does, it connects the extrinsic information about curvature with the intrinsic information about curvature. So let's continue on and unpack this a little bit to see exactly what we have. To see what we've got here, let's limit the discussion to 2 dimensions and consider just one of the components of our Riemann tensor. So we're going to look strictly at R1, 2, 1, 2. Lambda and alpha are 1, omega and beta are 2. So that's going to equate to B1, 1 times B2, 2 minus B21 times B12. Okay, again, considering only in 2 dimensions, what do you recognize about the right-hand side? Well, this is just the formula for finding the determinant of a 2 by 2 matrix. This would be the product of the diagonal terms. This is the product of the off-diagonal terms subtracted from this one. That's just the determinant. So this is equal to the determinant of our curvature tensor with both indexes in the lower position. Okay, well, what we've got here is a scalar relationship. This is a scalar value, this is a scalar value. But it is not an invariant scalar expression. And how do we know that? Well, that's because the determinant of a matrix with indexes in the lower position is a relative tensor. It's not an absolute tensor. So to rectify that, let's do this. Let's note that B alpha beta is really equal to S alpha omega contracted with B omega beta in this form. So this is the way we would lower the index from here to here. So these are equivalent expressions. Now, if you remember the multiplication property of determinants back in video 46, we know that the determinant of a product is equal to the product of the determinants. So the determinant of B with the two indexes in the lower position would be equal to the product of the determinants of S in the lower position here times the determinant of B with one index in the upper and one index in the lower position, like that. Well, our determinant of S with indexes in the lower position is nothing but the square of our volume element. So this is S times the determinant of B with indexes in the upper and lower position. So we can equate this then with this expression being S times the determinant of B in this form. Well, where that takes us is that we can now divide both sides of this expression by S, and we come up with this, that R 1, 2, 1, 2 divided by S is equal to the determinant of our curvature tensor with an index in each position. Now, this time we have an invariant expression because we know that this determinant is invariant. When we have an index in the upper position and lower position, the determinant is a tensor. It's an invariant expression. And in addition, from video number 79, we know that this determinant is also equal to the Gaussian curvature. So we now understand that this particular element, this component of our Riemann tensor in 2 dimensions again, divided by the square of our volume element, will give us the Gaussian curvature of our manifold. And that tells us that we can compute the Gaussian curvature of our manifold without any reference whatsoever to the extrinsic elements. This proves once and for all that the Gaussian curvature is an intrinsic property, and it's something that can be calculated directly from the metric tensor without any reference to any extrinsic elements whatsoever. Well, based on this information, we can now derive a couple of additional relationships that are a little more suitable for use in tensor calculus equations. So let's do that, and then we'll be done. In video 84, we explored the symmetries of the Riemann tensor. In the process, we discovered that for 2 dimensions, there's really only 1 degree of freedom. Remember, there are 2 to the 4th, or 16 different components, but 12 of them are going to be 0, and the other 4 are either going to be equal to this component or the negative of this component. Well, this expression captures that relationship perfectly. You can play with it a few minutes and see that it works. But even though it's correct, it's not the best expression. I mean, here we have a tensor, but none of these factors are tensors. So we can improve on this. And let's do it this way. We're going to write it this way. We're going to add a factor of the square root of s with each of these 2 factors. The square root of s times e lambda omega. And we'll add a factor of the square root of s to the second factor, e alpha beta. And then to accommodate that, we're going to divide this last factor, r1, 2, 1, 2, by s. So by multiplying by the square root of s twice and dividing by s, we keep the expression intact. Well, now we do have tensors for each factor. This one we now know is equal to the Gaussian curvature. So this is kappa. And then each of these 2 are the definitions for our Levi-Civita symbols. So this is epsilon lambda omega, and this is epsilon alpha beta, and that is then equal to the Riemann tensor, r lambda omega alpha beta. So now we have a tensor expression in which all of the factors are tensors. Not only that, but we've eliminated any hard-coded references. We don't have any hard-coded indexes at all. Everything is a variable index, and so that's much more appropriate as well. Okay, well, now you'll remember that expressions like epsilon lambda omega times its counterpart with the indexes in the upper position is equal to 2 factorial. So if we multiply both sides of the equation here with the counterparts with the indexes in the upper position, we're going to introduce a factor of 4. So we can then write the expression for the explicit value of kappa as being equal to 1/4 of epsilon lambda omega and epsilon alpha beta in the upper position times the Riemann tensor. Okay, all of this should remind you of what we did in dealing with determinants. There's a lot of similarity here. So we now have expressions that are much more appropriate for tensor calculus. Okay, let's take a break here then and end the video with a recap. The first thing we did was to apply the commutative operator to the shift tensor. And by finding both the normal and the surface projections of that result, we were able to come up with two very important relationships. The first is the Codazzi equation here. And the significance of this relationship is that it is symmetric with respect to the first two indexes. We can flip alpha and beta without altering the value of the expression. Well, we also know that the curvature tensor is symmetric with respect to these two indexes, and that means that the expression itself is totally symmetric. We can flip any two indexes in this expression without altering its value. The second expression we derived was the Theorema Egregium, and this is a theorem that makes a connection between the extrinsic curvature tensor and the intrinsic curvature tensor. It first of all confirms that the Riemann tensor carries curvature information about the manifold, and then it makes this connection between the extrinsic objects and the intrinsic objects right here. Now from this expression, knowing values for the curvature tensor, we were able to derive each of these expressions. We now know that the Gaussian curvature is equal to this explicit value because it's equal to the determinant of the curvature tensor with an index in the upper and lower positions. And from this, we were able to derive each of these other two expressions. Now of these, this is the expression that gives us the explicit value for Gaussian curvature in terms of the Riemann tensor by itself. So let me finish up with a couple of additional comments. We've emphasized the fact that Gaussian curvature is an intrinsic property. All we need is the Riemann tensor, and our buddies Bert and Ernie can figure out what the intrinsic curvature is just by looking at the metric tensor. Well, what we haven't said much about, though, is what's not available to them. Now, just because we know the Riemann tensor, we know the metric tensor, that doesn't lead to a unique solution on this side. There may well be many different types of surfaces that produce the same metric tensor. Such combinations would be known as isometric manifolds. They have the same metric even though they're not curved or embedded the same way. We've already run into that. For example, a plane and a cylinder are isometric surfaces. One is obviously curved and the other is not, but the intrinsic curvature is 0 in both cases. So what that means is this, that if we take a surface that is flexible and we begin to bend it and move it around, as long as we don't stretch the surface, we're not changing the metric tensor. And by not changing the metric tensor, we're not changing the Riemann tensor here, and we're not changing the intrinsic curvature. The intrinsic curvature is dependent only upon the metric tensor and not upon the way that the surface is embedded in the ambient space. So the example I like to use is that of a contact lens, the very soft contact lens. It has a curvature so that it will fit the surface of your eye well. But you can squeeze the bottom of it and form a shape that's long and thin, or you can reverse it. You can turn it inside out. And none of those actions change the metric tensor, and therefore the metric tensor nor the intrinsic curvature, the Gaussian curvature, will not change as that shape changes. And that's perhaps the most remarkable thing about this theorem. And I'll leave you with a quote from Gauss himself. He said that if a curved surface is developed on any other surface whatever, the measure of curvature in each point remains unchanged. And that perhaps is the most remarkable thing about this particular theorem.